Hello, this video will show us during the throttling process what happens if we have Freon going through the throttling valve and what happened to the temperature. Does that drop dramatically? That's what we want to achieve. And so through this example, we will understand how throttling works for refrigerant. So here's the example. We're going to draw a throttling device. And we have some kind of restriction, either adjustable valve or porous plug or anything. So this is R134 going through the pipe. And initial at the inlet, it said that it's going to be saturated. I believe it's actually going to be, let me double check. It's saturated liquid, okay. So it's a saturated liquid coming. And the given pressure is 0.8 megapascal. Then at the outlet, we know the pressure is going to drop after this plug. The pressure is dropped to 0.12 megapascal. Then we want to find out what's going to be the temperature drop. Okay. So the first step we're going to go to is find the governing equation for throttling device. We're talking about, in the last video, it's going to be H1 equal to H2. This we call isenthalpic process, which means enthalpy stay the same. It's a very simple equation, and it's actually so beautiful. You H1 equal to H2, then you can actually see how magic works here. So then, knowing that, we're going to find out H1. If it's a saturated liquid and given the pressure, so we're going to go to the refrigerant table. And it's saturated and it's given the pressure. So we're going to look at our table A12. So from table A12, and it's 0.8 megapascal. In other words, it's 800 kilopascal. At 800 kilopascal, what do we have for our H1? So it's this row, and let's take a look at our H1. So H is this one, and it's a saturated liquid, so we're reading HF. So it's 95.47. kilojoule per kilogram. So once we find out our H1, we can equate H2 equals the same value because it's throttling device. H1 is equal to H2. So knowing that, we can put that information on here because that's outlet H2 95.47 kilojoule per kilogram. Now for the state 2, for the outlet, we know the two properties now. We not only know the pressure, we also know the enthalpy. So knowing that, we can go ahead find our T2, right? Actually, before we do that, we also needed to find our T1 because delta T is going to be final T2 minus T1. So what will be the temperature initial? Oops, I think I'm going to write down here. So T1. What's T1 value? So we can go back to the same table, the pressure table at 800 kilopascal, and this time we're looking at a T, and the T is right here, right? So it's 31.31. That's going to be our saturated pressure. at 800 kilopascal. That's 31.31. Okay. That's in temperature, degrees Celsius. That's our T1. Now, we're going to figure out our T2. So T2, going back to our discussion earlier, you know two properties. You know P and H2. So first thing we're going to go is determine what state is this. Is that superheated? Is that subcooled? Or another word called compressed? Or is that a saturated liquid vapor mixture? So in order to find out, we're going to go to the pressure table, 0.12 megapascal. That means it's 120 kilopascal. So going back to the same table A12, and the second property is 95.47. So let's go to H, which is right here. And HF is 22.49. HG is 236.97. Our value is 94.47. It's in between them. So we're going to say from table A12, we realize HF at this particular pressure, which is 0.12 megapascal at 120 kilopascal. Our HF is 22.49. And our HG is 234.44. And this value you have H2 is 95.47. You calculated from the previous step. That's between the HF and HG. That tells us this is going to be a mixture, right? So if it's a mixture, I mean, we can potentially find a quality, but they didn't ask the quality. They want to find the temperature. So we can directly go figure out what will be the temperature. So what is the saturated temperature at this time at 120 kilopascal? So let's go back to the table. At 120, the saturated temperature will be this value, negative 22.32. Pretty low temperature, right? That's your T2. Since state 2 is a saturated liquid vapor mixture, so that's our T2. Now our final step, we can find our delta T, the temperature drop, final minus initial. Our final temperature at this low pressure, it's negative 22.32, and initial temperature, it's 31.31. Well, when we calculate that, that will give us negative 53.63 degrees Celsius. That's how much temperature has dropped in this expansion valve. Pretty interesting. So you have high pressure going through this porous plug, getting down to this low pressure. So not only pressure drop, accompanying this pressure drop, we have this big temperature drop, and that is desirable for refrigeration. Okay, so that's all for this example. Next video, we're going to look at throttling valve one more time using different substance instead of using R134. Okay, see you next time. Bye.